Hey, welcome back. In this video, we're going to tackle a singular example of modeling with trigonometry. This video is built on the idea that you already know basic transformations of functions and you have a general concept of the graphical structure of sine and cosine. Our example here is the outside temperature over a day can be modeled by a sinusoidal function. That's simply meaning we can use sine or cosine to model it. You know the high temp of the day of 52 degrees occurs at 4 p.m. and the daily average temperature is 45 degrees. We're being then asked to find the temperature at 7 a.m. Importantly here, we first need to develop a function that models this information before we can answer this question. There's a few very important things when I'm looking at this. So the outside temperature over a day can be modeled by this function. Importantly for me, what that means is the period of this function equals 24. So we're going to have to make a horizontal adjustment to our sine or cosine function so it completes one full shape instead of in 2 pi in 24 hours. And then we're also told that we have a high temp of the day at 52 degrees, and that's at 4 p.m. Both those pieces are going to be really important, is the 52, but also that it happens at 4 p.m. And then we're told that the daily average is 45 degrees. One of the first things I find that students struggle with when modeling with these trigonometric functions is to decide, for instance, well, when am I going to use sine? When am I going to use cosine? Honestly, because sine and cosine are almost identical, they're just shifted versions of each other, you can always use both for the application, though there's very clear ways that delineate which one you should use. And that delineation is about the information you're giving about how you're going to have to shift this model. Importantly here, I'm always talking about sine. If I'm given information at a specific time or specific point about the equilibrium or something that occurs on the midline. In this application, the midline is this average temperature of 45. So if they said at some point, your average temperature, the average temperature is reached at 1 p.m. or something like that, I would use sine. But in this case, I'm going to use cosine because cosine starts at a maximum value. I also can make it start at a minimum if I vertically flip this. But I'm going to use cosine to model this specifically because this high temp of the day is 52 at 4 p.m. But I'm going to come back to that. Really, most of the investigation of this information does not require that I choose sine or cosine, but I just wanted to talk about why I'm going to use cosine here. And again, the reason I'm using cosine is I'm given a specific max temperature at 4 p.m. and cosine is related, or the starting point is at a maximum value. So first and foremost, I'm going to work with this period being 24. If the period is 24, I can find this important b value that makes this horizontal stretch or shrink action going on by using this relationship that the period is equal to 2 pi over b. By multiplying by b and dividing by 24, I can turn this equation into b equals 2 pi over 24. And then I can reduce that by dividing that by 2, get a 12 and a 1. And I get that b is pi over 12. The second thing I'm always going to look at is my amplitude. The amplitude is how far this function ranges from the midline. You can always take the max and the min and then find the average of that to find the midline. But in this case right here, if I want to find the amplitude is going to be the difference between this max of 52 and this average of 45. So we have this midline or this average temperature. We go all the way up to 52. That's actually going to be a difference of 7, but just to show that math, the amplitude, which is our A coefficient in our general form, will be the 52 minus the 45, and this gives us 7. Third up, I want to talk about the midline. The midline for an untransformed sine or cosine function is always here at 0. So the question is this kind of average that runs through this function, where do I want that shifted? And they've clearly said it's at 45. So the average is at 45. I want to vertically shift my model up 45. So that's our D coefficient, and that's going to be 45 given to us directly. And the good news is that's really most of the work. What I've done, just to quickly review, I have my period of 24. I'll get that if I use a B value, which is this horizontal stretch shrink factor of pi over 12. It's always straightforward using the pi equals 2 pi divided by that B value. I found my amplitude. In this case, I just investigated the difference between the maximum and the midline value, because that is, by definition, what amplitude is. My midline, which is this vertical shift, is 45, so I get that midline of 0 up to 45. And I decided on the cosine function, I'll really hit more on this because I've been given this max or high temp. So as of right now, what I have as a model is 7 times the cosine of pi over 12 times x plus 45. Now, the important thing I need to do is actually use this information right here directly. This will give me a point to base everything on. And again, I've chosen cosine because this is a max value at a specific time. But just real quick, before I make that final adjustment, I think it would be useful to look at a graphical representation of the current function that we have now. If you look at this, and I projected this dotted line across at 45, which is our average temperature, and we do have this max, it starts at 0, this maximum of 52, then halfway through or at noon, I'm at this minimum value, and then back to the max at the end. And again, in this case, as I'm showing this, I'm just graphing one 24-hour period. The important thing going on here is that I don't want that maximum value to be at 0. I want that maximum value to be at 4 p.m. It's really important, and hopefully you can see this graphical representation. The hours are represented from 0 to 24. 0 being, let's say, midnight, and 24 being the next midnight. So one full day. Noon is 12, but 1 p.m. is 13, right? Because it doesn't start over from 12 to 12. We don't do that on a rectangular coordinate system. So importantly right here, when I see 4 p.m., given the way I'm going to model this, I think of this as 1600 hours, or at hour 16. It's like military time. So what I need to do now is I need to make this happen. So the max of 52 degrees occurs at x equals 16. And again, this is a little hidden kind of thing that could frustrate you. But again, I'm using 16. That's 16 hours after midnight, which is what 4 p.m. is. To make that adjustment, all I need to do is take that graph I just had up here, and I need to horizontally move it to the right 16 units. And I can make that adjustment by simply subtracting 16 from the x value here. And so actually our final model for this situation is 7 cosine of pi over 12 times x minus 16 plus 45. And importantly, just to recap all of these pieces right here, this 7 gives me my amplitude. This is the distance from the midline. The temperature will vary 14 degrees throughout the day. It's always double the amplitude, but this is the distance between the max and the midline. This interesting factor right here, pi over 12, simply just gives me a period of 24. It stretches this function so it covers one period in 24 hours. This minus 16 is what gets this max temp at this point. I don't need to do anything with the 52 when I do this, because that's already incorporated into the midline and the amplitude. So it'll already go up to 52. I just want to make it occur at this point, which is this subtraction of 16. So this is a shift right of 16. And again, I should say this is the period of 24. And then this 45 right here is simply the average temperature, or that midline. And that's really the work of the question, but I can't forget to answer what has been asked of me in the very beginning. I'm being asked to find the temp at 7 a.m. I have now a complete model I can plug in any time. I don't need to make a crazy adjustment to this time because it's 7 a.m. It would just be 700 hours, or 7 hours after midnight. And so simply, I'm just going to take my calculator out and plug in 7, making sure that I am in radians. This adjustment of the period is only true if my calculator is in radians, but I plug that in and I got 40.05 degrees at 7 a.m.